effectively near the second half of our last topic. So I've got one more problem to do on indeterminate beams, and then we move across to indeterminate axially loaded structures. Then we might even start on revision straight away, and in the last week you'll be getting your test papers back next week in your practice class sessions. I don't provide solutions to those, so in the last lecture, that's next Wednesday next week, or in the second half of that lecture, what I may do is half of you will have got your tests back. The other half I might bring them with me to the lecture and you can look at it, and then maybe in that last hour I will go over the test questions. And I suppose that would be an optional if people got a 10 out of 10 for those questions, got 10 out of 10 for the test, then you could mosey off and leave everyone else behind to get work. But we'll confirm things anyway, but we're doing well with our timing. Okay, indeterminate beams, let's go back. So that was the case where you had beams such as this one here, where you can see here we have, oops, and I haven't got it on pen mode yet. Well, you can see here you have 1, 2, 3, 1, 2, 3, 4 unknown reactions. Shh. So equilibrium is not enough. We need to use compatibility as well. So we worked through that last week and we got to our final problem, which was this beam hanging from a rod. So looking at this problem now, we have a steel beam here and rod used to support this load of 8,000 newtons. If we look at our reactions, at A we have 1, 2, 3 potential unknown reactions, and at C, now this is a pin support, so in theory it has a horizontal and a vertical reaction, but because this is a rod and effectively there's a pin connection here and a pin connection here, we know this rod can only carry axial load. So we have 4 unknown reactions. So we know that equilibrium on its own is not enough. We have to use compatibility as well. So what are we told in the question? It is required that the allowable normal stress for the steel is 130. So basically our yield stress is 130 MPa, and thus our My on I will have to be less than or equal to our yield stress. We're also told the maximum deflection, so the maximum deflection will occur here at B. So this deflection at B has to be less than or equal to 1 millimetre. So looking at these two conditions, it means we have to satisfy both. We don't know if it's going to deflect 1 mil before it reaches yield, or it reaches yield before it deflects 1 mil. So we're going to have to make an assumption when we do this problem and then check the assumption we made is correct. So we're told that the beam here is a 100 by 60 millimetre rectangular hollow section. So if I cut through here, XX, this is my section XX here. So thus we can work out our moment of inertia. And the question is asking us to determine what area this rod has. It's a rod, so effectively we want to know what our radius or our diameter of our rod is, such that with that loading on, we don't overstress the rod or the beam, and the deflection here is not more than 1 mil. So is everyone clear about the problem? Clear as mud. Just going to put this up. Isn't that great? It's down really low. Okay. Okay. So let's firstly work out what our moment of inertia is. As I said, this is a 60 by 100 mil section, and I'm going to work in metres. So I'm going to work this out. BD cubed on 12, which gives me an I value of 5 by 10 to the minus 6 metres to the power of 4. Now, Have we been given useful, have I shown you useful information? Here's our useful information down here. Let's go back here. So in terms of coming up with a determinate system, which unknown will we take away? I think it's pretty obvious here. We're going to take away the support provided by the rod at C. So what we're going to do is we're going to split our system into two free body diagrams. So what I'm going to do is I'm effectively going to consider that as one free body diagram and that as another. Shh, I can hear you. Okay, so even splitting it in two, we still here would have four unknowns, so we're going to consider our primary system to comprise no support at all, just our 8,000 newtons. Then we are going to put back what we took away, which is our reaction. I'll call it CY. This is our redundant. And as in this previous problem, let's go back to this problem here. Remember we said the primary plus the redundant is equal to the deflection provided by the beam support. This time round we are going to say our primary, let me just write in red here, this primary will deflect down an amount delta primary, this redundant will deflect up an amount delta redundant, and thus our compatibility we'll say our primary deflection plus our, we won't worry about signs as yet, our redundant deflection is equal to the, what do I call it? I'll call it the stretching in BC. And what is the stretching in BC equal to? Remember the formula from way back? The amount of stretching here is equal to PL on AE. So therefore, this is all equal to P. And what is P? Well, it's the force. CY times L on AE. So this is our PL on EA. AE. Is everyone clear with that? About that? So, what is our primary deflection equal to? If we do go back now to this useful information, where do we want the deflection? Here you'll see we want it where the load is applied. So which formula would we use, A or B? A, cool. So we're going to use this equation here, which tells us the deflection under the point load. So thus, in here, our deflection, it's downwards. The formula was PL cubed on 3EI. So that's equal to minus 8, I'll leave it in kilonewton, times our length. This length here is 1.2 metres. 1.2 cubed on, we're given the value of E. And the I value we worked out here, 5 by 10 to the minus 6. And the E value in giga, we want to write it. We're currently working in units of kilonewton and metres, so we want this E value in kilopascals. So how do you get from giga to kilo? What's this multiplied by? 10 to the 6. Good. So I'll put a 210 by 10 to the 6 in here. Now when I look at my redundant deflection, sorry, I'm writing right above that so I can't write it out. Once again we want the deflection under the point load. But this time our point load is CY. So it's again PL on 3EI, but this time our P force is CY times your 1.3, 1.2 to the power of 3. I'll just write it as 3EI here. So looking at our entire equation now, next page, primary, plus redundant is equal to CYL is 1.5 metres on EA. Because these two equations were the same, I can simply write it as minus 8 plus CY L cubed on 3EI is equal to. Now, down is negative, and you can see here this thing will stretch and there'll be a downwards movement, so I need to put a minus sign here in front of the movement downwards in our compatibility equation. Now, just taking our e's out as our common factor, you can see we have a formula here in terms of CY on both sides of the equation and in terms of A. So in this equation here, we have two unknowns, CY and A. And this is now where we are going to have to make an assumption. And at this point here, we will assume that our rod BC reaches the maximum yield stress of 130 MPa, because we need a second equation. And in making that assumption, we're saying our yield stress, which is equal to 130, I'll write it in kPa because they're the units we're working in, well, that's equal to CY divided by A. So this equation up here is equation 1, and this equation is equation 2. Now let me just check. Okay, I have got another blank. So now, substituting equation 2 into 1. Hopefully you can all do that maths yourself. Yields a value of CY equal to 6.3 kilonewton. So we now have a proposed force that will be in that cable, and we can work the area out. But before we do that, we need to go and check that the stretching of BC is less than or equal to 1 millimetre. We need to check this as well. So, based on this equation here, we can work out our stress 130 is equal to our CY force of 6.307 kilonewton divided by our area. So thus from here, our area has to be greater than or equal to 48 millimetres squared, which is equal to pi r squared. So thus our radius has to be greater than or equal to 3.9 mil. So we're looking at an 8 mil diameter rod here, okay? 3.9, you'd go in there, you'd go, okay, what can you buy? 6 mil, 7 mil, 8 mil, you'd pick up an 8 mil rod. So thus, let's check the deflection of BC is now less than 1 mil, based on a 4 mil radius, 8 mil diameter rod. So delta is equal to PL on EA. And we cross our fingers. Now I'm going to work in newtons again. PL on E times, I'll just put in my original area. And that gives us a deflection of 0.93 mil, which is less than 1 millimetre. Therefore, we're okay. So provide an 8 mil diameter rod. Now if you found it was deflecting too much, you would have to have set this equation here. So if the deflection was found to be greater than 1 mil, you would set 1 mil equal to your PL on EA, and here solve for P, which is equal to CY, and then once you got that value in your stress equation, you would then check that the beam is not being overstressed and the column is not being overstressed. Now as yet, I haven't checked the stress in the beam, have I? So we checked the stress in the rod here. We equated that to 130 MPa, but we still need to check the beam is not being overstressed. So how do we do that? From our bending moment diagram, of that 8 kilonewtons, we know that 6.3 is being carried by the rod, and so therefore we have 1.7 kilonewton being carried by the beam. And thus we can work out that maximum moment here. And based on that maximum moment, you can work out my on I. You can work out my on I. I'll do that over the page. Hang on a minute. I'll just save that. Excuse me for not putting another one in there. So let's be clear what's happening. We have a beam, apologies again, this pen. We have a beam here with 8 kilonewton on it and a rod. And what we have is we have the rod carries 7.3 kilonewton, and so thus the beam itself is carrying your 1.7 kilonewton. So 1.7 in beam, and I should turn this around and say rod carries 6.3, and this adds up to our 8 kilonewton. So the bending moment diagram here looks like so. It's triangular, and our bending moment here would be 1.7 kilonewton times 1.2 metres, which gives us a moment of 2.03 kilonewton metre. So now, when I work out my on I, that's my moment, and I'm going to convert to Newton millimetres times y. And what is y? Remember our beam is 100 mil deep. So y is equal to 50 mil, half the section depth, and I is equal to your BD cubed on 12, which if I convert back to millimetres to the fourth is equal to that. That gives me a stress in the beam value equal to 20.3 MPa, which is less than 130, so therefore our beam is okay. So our beam's not overstressed, our rod's not overstressed, we're deflecting less than 1 mil, and that is the problem solved. Any questions? Okay, that brings us to the end of indeterminate beams. And we now can move over on towards indeterminate axially loaded members. Any questions? I'm still getting project questions, so we could have a 5-minute session in here working on project questions if you wish. Oh, okay, we'll move on to indeterminate axially loaded. So let's run through again so you clear where we're at. We have spent about 10 weeks on looking at determinate systems, calculating reactions in trusses and beams, and everything's been determinate. Now we're looking at indeterminate structures. We've just dealt with beams, and now we're going to look at axially loaded structures. So again, what are these compatibility relationships we're talking about? Compatibility consideration requires us to look at the internal deformations and or the external displacements in a system. So it allows us to look at, means we have to look at how the structure fits together, how that we can't have gaps or overlaps in things. So here is an indeterminate axially loaded structure. We need to look at the simplest possible case of axially loaded members, where we can cope with one extra unknown value. So an axially loaded member is the simplest possible case. When things get more indeterminate, when there are more unknowns, it's basically too complicated to do by hand in first year. So you'll be learning techniques looking at matrix methods in second and third year, how to assess things that are very indeterminate. And at the end of the day, who does the number crunching for you? The good old computer does it. So you would stick a model in and the computer would analyse things for you. But in order to understand what the computer does, it's good that you can work through by hand and see what it is the computer's doing. Okay, so indeterminate axially loaded members. If we looked at an indeterminate axially loaded member, fixed at both ends, you can see that we have 6 unknowns. We can't cope with 6, we can only cope with 3. Now, because our loading is axial, we know we don't have any horizontal forces. So thus we know dx and ax are both equal to 0 by virtue of the fact that we've only got a vertical load. And in effect, we've now used up one of our equilibrium equations, but one equation got us 2 unknowns out of the picture. Then again, because our member is axially loaded, is our member bending at all? No. So we can therefore say we know that there are no moments at the supports too. So that in effect, by saying that, we've used up our moment equilibrium equation. We've got rid of another 2 unknowns, but using another equilibrium equation. So now we've only got one equation left. All the forces in the y direction equal 0, but we still have 2 reactions to deal with. So once again, we're short. We're indeterminate by 1 degree. So we need one more piece of information. So in all those beams we were looking at, we had 4 unknowns, 3 equations of equilibrium, 1. So you'll only be given situations where you have 1 degree of indeterminacy, basically, where you have 1 too many reactions to calculate and you just need that 1 extra equation. Okay, So what do? We need compatibility. So let's look at what the compatibility is this time. So what do is we identify axial deformations that are the same, i.e. compatible, for those sections with different forces. So in this problem here, one could say that the amount of movement stretching in BD here, well, that would have to equal the amount of compression, amount of movement squashing occurring in AB. Because you can't have one bit stretching more than the other when the two ends here are fixed. So in this case here, that would be your compatibility equation. And because we're talking axially loaded systems, we know the movement we're talking about are in terms of PL on AE. So people think this here is the compatibility equation. It's not. The compatibility relationship is the relationship between two unknowns, and instead of delta stretching or squashing, we're using the known equation, PL on AE. So that's how we tackle these axially loaded problems. So in what we just dealt with, beam bending, we equated two deflections, and we had the beam bending formulas we utilised. Now we'll always do it in terms of PL on AE. And that last problem I just did, that was also in terms of one of the stretching forces, one of the movements was a stretching in terms of PLAE on AE. Okay, so this relationship, this equation here should ring a bell. This is the equation that tells you how much something will stretch or squash experiencing an axial load of P divided by the material's Young modulus, that's the material stiffness, and the cross-sectional area of the member. We all know if something is fatter, it won't squash as much. So down here in the denominator, is that the denominator on the bottom? Yep. In the denominator, if that value is bigger, you can see we're going to get less movement in our change in deflection. Okay, now in tackling these problems, there are two ways, what I call the direct method and the principle of superposition. In the simpler problems, the direct method is the quickest, the easiest. But when you get more complicated problems, I find the principle of superposition by far the easiest method. So I'll be showing you both methods, and when we get to more complicated problems, I'll only use this principle of superposition. Okay, we have a member. It has an 8 kilonewton force. That force is loaded 3 metres down, not in the middle. Which support will carry more load, A or D? A, because the force is closer to A. Okay, so equilibrium in the y direction. We know that AY and DY plus DY minus 8 equals 0. Force equilibrium. Now, when it comes to axially loaded members, I want you now to draw these unknowns in their true direction. So we're drawing both of these forces up, and if you then look at a free body diagram of AB, you will get a downward force. So that's telling you that AB is in compression. And if you look up here, because that force is up and this force is down, this will get you a stretching in dB, so you'll get a tension. So now no longer is negative mean compression and positive tension, okay? We're looking just at the reactions here. So here I've got it here. So note from the free body diagrams of BD and AB, so free body diagrams through here and through here, we are going to equate our AY, our reaction at A, equal to the force, the internal force in the section AB, and we are going to equate our reaction dy to the internal force in BD. And so our equation, even though we started off looking at it in terms of reactions, can be written in terms of internal member forces. Whether you choose to write it in terms of reaction or internal member forces is up to you, as long as you know they are one in the same, they have one in the same value. Okay, so we have one equation, and now we need to look at our compatibility. And our compatibility here would say that the elongation in our top part, dB, well, that's equal to our contraction in AB. So these two deformations are the same. So now when we write them in terms of PL on AE, we put the corresponding P force as the internal member force. Because the force in here is force BD, and the force in here is force AB. So when I write PL on AE now, I'm looking at the corresponding force in section BD, the length of section BD, which is 3 metres, on AE. And I get that second equilibrium equation. And now, so in this case now, we don't deal with negatives and positives anymore. We're looking at absolute values. So we just equate the two absolute value, the absolute value here, in effect, and we don't bother with negative signs anymore. So that's why I've written the comment, why isn't the deflection dB equal to negative deflection AB, since one's contracting and one's elongating? It's effectively because we define both our internal forces as positive, even though one is a compression. So we're dealing with absolute values. So here are our two equations of equilibrium. Well, one equation of equilibrium and one equation of compatibility. We have two unknowns, and thus we can just solve for those two unknowns. Now, easiest way to solve, people have trouble. Do we do simultaneous equations? No, just rearrange one of your equations. So you make one of your unknowns the subject, okay? And then substitute that value into your second equation. So if you choose to solve simultaneously, you can do it that way, but that's the usual way to do it. And here are our two internal forces. So down here, our reaction at A, our force in member AB is 4.8 kilonewtons. That's where the majority of the load is. And at the top, we're looking at 3.2 kilonewtons. So when you're asked these questions, you're usually asked, what are the reactions? And just what you have to realise is, when you write them in terms of the reactions, you're really relating them to the internal forces. And once you know the value of these forces, we can then, it says calculate the displacement at B. Well, you can then back substitute into your PL on AE equation, and regardless of which one you substitute in, you will get the same value. So this point here is moving down an amount 9.6 on AE. So far, so good? Okay. So now I'm going to show you the same thing, and when I just explained using that method, I was going, oh, it's absolute values, don't worry about negative signs, don't worry about positive signs. Slightly confusing for me to explain it to you. When we look at superposition, we can actually see what's happening. So we don't have to pretend or forget about signs. So remember, what is the principle of superposition? It states that the effects of each load can be calculated separately and added together to obtain the effect of all the loads applied together. So I have an indeterminate system. I'm going to turn it into two determinate systems by removing one of the supports, which is exactly what I did for indeterminate beams. So in this case here, I'm going to remove the support at A. Now looking here at this system, this is now determinate. I can easily calculate that stretch in there because that will just be equal to PL on EA, will it not? Okay, and when I take away a support, I have to put it back. And again, I can calculate that shrinkage now. This time my P force will be FA, and this force here, can you see, is travelling up the entire length. So this time L is 5 on AE. Now back here, let me just rub that out. This value here, this time here, this deflection here, our force is 8 kilonewtons. And where is that force travelling? Is it travelling down here towards A? Isn't it just going up here and being resisted at the top? So when you work out your length here, what is the length over which the load is applied. It's just 3 metres on EA. Can you all see that? So you look at your system and you ask yourself, what's happening? I have an 8 force. It's causing only BD stretches. So thus, when we use our formula, our length here is only the length of BD. When we apply our force back, it's the entire length now squashes. So thus our length is 5 metres. So I have 2 determinate systems that make up one indeterminate system based on the compatibility relationship. And what is that relationship? What is our deflection at A equal to? Well, it's 0. It's a fixed support. So thus, just as I did with beams, I can say my redundant deflection and my deflection, I don't know why I've called it A here, at A, now equals 0. So, as I said, based on those 2 terms, I just add them together, and you can see this term here is in terms of our unknown FA. Now, once again, you can tell yourself this is a stretching, so this will be a positive value, and as drawn, this pushing up is a compression, it'll be a negative value, and then you just solve for FA. Make sense? Putting you all to sleep? Okay, do this one then. Now, this is one I would find difficult to explain to you not using the superposition. Because if you attempted to use the direct method, you would say, okay, well, the stretching in BC plus CD is equal to the stretching in CE, but I've got different areas to deal with, and things start getting a bit messy. If you want to use that method, you can. I vote for superposition. So, what support do you want to take away? B or E? B. Good, that's the way I've worked out the solution. Okay, and I've got it on eraser. We don't want that. So, we are going to take away the support at B. And we'll just call this amount of stretching here delta primary, and that amount of stretching is due to this 80 kilonewtons here. So what is delta primary equal to here? PLNAE, 80 times 2 on our areas A, we'll just call it EA. So that's removing support B. So now we are going to put it back. Now remember when you, and my drawing's not very good, we'll call this BY. Okay, we're going to put it back now, and we're going to calculate delta redundant. So what is delta redundant equal to now? I have a change, a difference in my area. So I'm going to break this up into the deflection in BC plus the deflection in CE. Now please take note, I'm not applying the 80 kilonewton here, I have to apply it once, because what I am saying is that that is effectively equivalent to my 2, this is meant to be a plus sign, to my 2 redundant systems based on the compatibility relationship that the 2 deflections equal 0. So let's go back. What is our redundant deflection equal to? Well, in BC, it's equal to PY times our length 4 on E, and our area is 2A. And then we have to add to that the amount of compression we get in CE, which has, can you see, this all has the same force in it, By. So once again, our force is By, our length is 4 metres again, but our area this time is just equal to A. So when you add those things up, you can see that 2 cancels out with 4, so you've got 2 plus 4. You get a value here of 6 By on EA. Thus, when we link those two determinate systems up using compatibility, we would now say 80 times 2 on EA. One's a stretching, so then we can take away our compression. Doesn't really matter which one you say is negative or positive. That equals 0. And from that, we get a force for By of 26.6. So of this 80 kilonewtons, 26.66 is being carried down there. And the remainder up here, 53.33 kilonewtons, is being transferred at the top. And if you do look here, in this determinate system, this first one where we move B, if I apply 80, this reaction here is equal to 80. And then when I apply a By, the reaction up here is By. So this 55 is actually equal to 80 minus By. And this reaction down at the other end here is just equal to By. I don't think I want to start another problem now. I'll just answer project questions and we'll continue this exciting topic on Wednesday.